So next we want to talk about measuring distance, line segments, and circles a little bit. So as we continue our informal investigation of the concept of distance, we notice that we want a line segment to be a path of shortest distance from one point to another. The 2 points are the endpoints of the line segment, and the other points of the line segment are between the 2 endpoints. So here's a little activity you can try out. Think of a flat surface, such as the top of a table or desk, as being a portion of a plane. Identify 2 distinct points on this plane. Stretch a string taut between the 2 endpoints so that the string stays in the plane. The resulting portion of the string from one point to the other is the shortest path from one point to the other. So this is a line segment. We can extend a line segment by appending another line segment end to end, so the resulting figure, union of the 2 line segments, is again a line segment. In other words, continue in a straight path. We can do this as many times as we want, so that we can extend any line segment to a longer line segment of any desired length. We can do this infinitely many times in both directions to produce an entire line. This is the idea behind Euclid's second postulate. All right. Here's another activity. Pick a string of a certain length. Pin down one end and let the other end move within the plane so that the string is always taut. The non-fixed end will trace out a path that includes all the points in the plane. One thing you can even try to do is even tie a pen or pencil to the end of the string, pin down one end, and trace out what happens. Now, this is a little bit difficult because the pen is going to, or pencil is going to have a tendency to wobble on you, but if you can keep that pencil vertical, perpendicular to the plane as you trace around, then it will trace out what we're talking about here. So the non-fixed end will trace out a path that includes all points in the plane, which are the same distance for this fixed endpoint. What do we call this shape? If you're not 100% sure what it's going to be, press pause now and actually try that experiment out yourself before you go on. Well, hopefully this is a pretty recognizable figure. It's a circle. So let's define what's meant by a circle in some related terms. A circle is the set of points in a plane which are a fixed distance, called the radius, from a given point, called the center of the circle. Notice that the center is not part of the circle. Okay, the radius is a number. Before I go on to the other definitions, let me remind you, definitions are very precise, and if you change something about the definition, you're either defining a different term altogether, or you or have something that's not well defined. But the point is that you've got to be sure that you're very careful about learning definitions. One of the most important things in mathematics is for us to learn the definitions, right? If you don't know the definitions of the basic terms, then how can you even get started? You know, it's like if you don't even know any of the rules of the game, how can you even begin to play the game? So memorizing definitions is always an important part of a math class. And again, they are very precise things. So for the most part, it's really hard to write the definition down unless you do it very precisely and you can't change any words. In my class, I will ask you maybe to restate some of these definitions. Now, one of the things that happens is geometry in particular has more than its fair share of definitions. So I strongly encourage you to get out some index cards, write the term on one side and the definition on the other side, and make yourself some flashcards. And you might also have a figure representing that drawing, an illustration representing that term, whatever it is, and then the term on the other side in your set of flashcards as well. So I strongly encourage you to make a set of flashcards and start memorizing these things. I will typically ask these as some quiz questions. So once again, a circle is a set of points in a plane which are a fixed distance from a given point. a line segment from one endpoint on the circle and the other endpoint at the center of the circle is called a radial segment. So it goes from the center out to the circle itself. That's called a radial segment. A line segment with both endpoints on the circle is called a chord of the circle, C-H-O-R-D, chord. A chord containing the center of the circle, we're going to call that a diametric chord. The length of a diametric chord is called the diameter of the circle. So, of course, the diameter is twice the radius. The length of a path starting on a circle and following around the circle back to the original point is called the circumference of the circle, the distance all the way around it. And the set of points whose distance from the center of a circle is less than the radius form the interior of the circle, and the set of the points whose distance from the center of a circle is greater than the radius form the exterior of the circle. Now, notice our terminology here, the way we're defining it, that the terms radius, diameter, and circumference are positive real numbers, lengths, right? Numbers. Circle, radial segment, chord, and diametric chord are geometric figures, sets of points. Note that it's pretty common that some people use the word radius for both a length, what we call the radius, and also a geometric figure, what we call the radial segment. Similarly, some people use the word diameter for both what we're calling the diameter, which is a number, and a diametric chord, which is a set of points. Of course, the diameter is the length of the diametric chord. We will avoid this problem of using the same word for two completely different things, related but different, completely different types of things, numbers and geometric figures. We're going to avoid that by using the definitions that we have here. In a formal analytic approach to geometry, such as the Birkhoff's approach, right up front we assume that we know all about the real numbers and their properties, and we have postulates that ensure the existence of measures for distances and angle measures. In particular, at the beginning, we establish a one-to-one correspondence between the points on any line and the set of real numbers in such a way that any line can be viewed as a coordinate system or as a number line. Following are Birkhoff's definitions and postulates related to distance and order. And this week we'll be adopting very similar statements in our formal treatment of unified geometry. Now recall, Hilbert's axioms of or postulates for order were dealing with synthetic approach, and then Birkhoff's here have some distance postulates. So he's going to have the term distance is undefined. The distance between any two points A and B is a non-negative real number such that the distance from A to B is the distance from B to A. Between, then, line segment and half line or endpoint, those are all terms that we're going to actually define, whereas between was left as an undefined term in Hilbert's approach. So if A, B, and C are distinct points, we say that B is between points A and C, and we denote that A-B-C, if and only if the distance from A to B plus the distance from B to C is the same as the distance from A to C. A line segment is the points A and C together with all the points B such that are between, so B is between A and C. And we use this notation AC with the little bar over it for with no arrows. That's for a line segment. A half line, or we'll call it a ray in our class, we'll call it the half line M prime with endpoint O is defined to be by 2 points O, and A in the line M. A is not O, so 2 different points, as a set of all points A prime of M such that O is not between A and A prime. And then we have a postulate of line measure. The points A, B, however many points, of a line can be put into a one-to-one correspondence with the real numbers x, so that the x number, the real number x of b, which is the coordinate of b, minus x of a, the coordinate of a, and then take the absolute value, is the distance from point A to point B. I guess this should be really, that should be a capital B and a capital A there for all points A and B. All right, so that's the formal way we're going to do it. Now we're going to introduce this a little more formally in our way of doing it in this this set of notes for this week, and it will be done in a very similar way to Birkhoff's thing. So this is our real one concession to an analytic approach. Most of what we're going to do is synthetic, but this is going to be something we're going to do in a more analytic way, more along the lines of the way Birkhoff set it up. Okay, so in the next few videos, we're going to be introducing four infinite geometries, Euclidean and 3 non-Euclidean geometries that we're going to include together as long as possible in unified geometry. As we add more postulates, eventually we will drop off one and then the other one and the other one until we're finally just left with Euclidean geometry. But we're going to prove as many things as we can that works in all the geometries as long as we can. And we'll do that by introducing some physical models for them as we go along. See you back for the next video. Things are going to start getting pretty interesting now.